Lesson 8. Lesson 8 is all about factoring by grouping. So number 1, factor the following polynomials completely. So we know it's grouping. It's a dead giveaway if you look at it and it's an x cubed polynomial and there's 4 terms. That's just shouting at you, use factoring by grouping. So let's look at the first 2 terms. X cubed minus 6x squared. Let's factor out an x squared. X squared times what gives me x cubed? X. What times x squared gives me negative 6x squared? Negative 6. All I did was I factored out a GCF from those 2 terms. The second 2 terms, I need to end up with an x minus 6 over here for this to work. What can I factor out? Well, I need a negative 25x and a positive 150. So if I factor out a negative 25, does that get me what I want? That gives me negative 25x. That gives me positive 150. Now look at this expression. This term has an x minus 6, and that term has an x minus 6. So we can undo the distributive property again and factor out that x minus 6. And we're left with x squared minus 25. But I want to factor completely. I always want to factor completely. So x squared minus 25, that's the difference of perfect squares. So we get x minus 5, x plus 5. X minus 5, x plus 5. So that's how I factor that first trinomial completely. Its factors are x minus 6, x minus 5, and x plus 5. I have 3x squared minus 5x squared, 3x cubed minus 5x squared minus 48x plus 80. Let's group the first 2 terms. 3x cubed minus 5x squared, I can only take out an x squared. There's no other common factor between 3 and 5 other than 1. I am left with 3x minus 5. Let's group these terms. I hopefully end up with a 3x minus 5. What's the GCF of negative 48x and 80? Well, if I take out a minus 16, I'm left with 3x, because 3x times negative 16 is negative 48, minus 5 times negative 16 is 80. So both of those terms have a 3x minus 5. I'm going to factor that out, and I'm left with x squared minus 16. Hopefully that warning light's going off in your head. X squared minus 16 is the difference of perfect squares. So we can factor that as x plus 4, x minus 4. And this is factored completely. Always get in the habit also of first checking, is there a GCF, before you jump right to factoring by grouping. If you forget to check that, always check your terms. Is there a GCF in any of these linear factors here? No, there's not. Number 2, determine if the expression can be factored with real coefficients. If so, factor it. So, can I factor these expressions? Again, a cubic polynomial with 4 terms, I'm going to look at, can I group it? So let's look at the first 2 terms. 4x cubed plus 2x squared. Well, I can definitely take a 2 out. X cubed and x squared, I can take an x squared out. I'm left with 2x. What times 2x squared gives me 2x squared? Plus 1. Can I get a 2x plus 1 from these 2 terms? Minus 36x minus 18. Well, I can factor out a negative 18, and I'm left with 2x times negative 18 is negative 36x plus 1. So, because both of these terms have a factor of 2x plus 1, I can factor that GCF out and get 2x squared minus 18. Now, this is the point where in the beginning I should have said this has a GCF. If you took out the GCF already, great. If not, look at that factor right there. 2x squared minus 18, take out that GCF of 2. And you're left with x squared minus 9. I factored a 2 out from that term. X squared minus 9, that's the difference of perfect squares. X plus 3, x minus 3. Get in the habit, though, of looking for GCF first, and don't do what I just did. Take out the GCF before you jump right into factoring it by grouping. But also notice that you can still factor it out halfway through the process of saying 2x squared minus 18. That's it. Both of those terms have a factor of 2. The second one, x cubed plus 3x squared minus 2x plus 6. There's no GCF. So let's try grouping. You can take out an x squared from those two terms and get x plus 3. So I want to get an x plus 3 over here. So I see I have a minus 2x, so if I factor out a minus 2, I get x. What times negative 2 gives me 6? Negative 3. Notice these are not the same. Those two are not the same. So I can't factor out a GCF here. I cannot factor this by grouping. No, we cannot factor by grouping. So either we simply can't factor this expression, or we can't do it by grouping. We're not sure. Next week we'll develop some tools that let's just kind of cheat and say, can I factor this expression? And we can find out then. So these two linear factors need to be the same because all we're doing is taking out that GCF, like we did over here with this 2x plus 1. Write the expression as the product of two binomials. Hopefully by now you know that product means multiplication, the multiplication of two binomials. A binomial is a polynomial with two terms. So I'm looking at this, and could you distribute it out? Yes, you could distribute the terms out, but we need to look for and make use of structure and say they both have a 3x minus 1. So let me factor that 3x minus 1 out, and what am I left with? Well, x plus 4. I could check my work by saying this thing is one whole chunk, and I'm going to distribute that in. I get x times 3x minus 1, and then I get positive 4 times 3x minus 1. So my final answer is 3x minus 1 times x plus 4. Product of two binomials. This is the product of two binomials, and they're both linear factors. Factor completely. So I'm looking at this expression here, and the first thing that jumps out to me is it has a GCF of an x. So I'm going to factor an x out, and I'm left with x cubed minus 4x squared plus 4x minus 16. Now, hopefully I can factor this cubic polynomial here. So I'm going to try grouping. I'm going to group the first two terms. I can factor out an x squared, and I'm left with x minus 4. And the second two terms, hopefully I end up with an x minus 4 term. 4x minus 16, the GCF is a 4. I'm left with x minus 4, which is good because both of these terms have an x minus 4, so that's a factor. I can factor that out, and I'm left with x squared plus 4. You always need to check, am I done? Well, x squared plus 4, that's the sum of perfect squares, so it can't be factored anymore. If that was x squared minus 4, you could factor it. But because it's x squared plus 4, we can't factor that expression. So our final answer is x times x minus 4 times x squared plus 4. 5. Consider the expression. Explain how you can use grouping to factor this expression completely, then factor the expression completely. So, looking at this expression, it's written bizarrely. I have x cubed minus 3x squared minus 6x squared plus 18x plus 8x minus 24. So, this expression is written this way for some reason. I notice that their x squareds aren't combined together and the x's aren't combined together. So, let's look at the terms pairwise. Let's look at each of these terms. X cubed minus 3x squared. What could I factor out from there? Well, I can factor out an x squared. And I have an x squared times x minus 3. Now let's look at this second set of terms. Minus 6x squared plus 18x. Well, I can factor out a minus 6, and I'm left with a minus 6x, and I'm left with x minus 3. That looks promising. And finally, the last two terms. 8x minus 24, well, I can factor out an 8, and what am I left with? Well, x minus 3. So it's just taking this idea of grouping and extending it to the next level. So looking at this expression, every term has a factor of x minus 3. So I'm going to factor that out, and I'm left with x squared minus 6x plus 8. But I want to factor this completely. So the linear term's clearly factored completely. Can I factor this quadratic term anymore? Well, the leading coefficient's 1, so what multiplies to 8 that adds to negative 6? Well, that's negative 2 and negative 4. So, factored completely, this expression is x minus 3 times x minus 2 times x minus 4. Clearly, it was left written this way so that you could look for and make use of structure and apply this grouping idea to it. Consider the expression 2x to the 6th minus 7x to the 5th minus 15x to the 4th minus 2x squared plus 7x plus 15. Explain how you can use grouping to factor this expression completely. Then factor it. So I'm looking at this expression up here, and I notice 2, negative 7, negative 15, 2, negative 2, positive 7, 15. So what if I group them in pairs of 3? I look at those 3 terms together. Is there a GCF I can factor out? Well, from the first set, I can factor out an x to the 4th, and I'm left with 2x squared minus 7x minus 15. From the second half, I want to end up with that trinomial, and I can if I factor out a negative 1. So it's taking that idea of grouping and just extending it to a larger polynomial. Both of these terms have a 2x squared minus 7x minus 15, so I can factor that out front. Again, we're just taking out a GCF. And we're left with this product. So great, we factored that expression, but we didn't factor it completely. Because now we need to look at each of these terms and say, can I factor it anymore? Well, this quadratic here, we can use the AC method to factor it. What multiplies to 2 that adds to negative 15? Well, that's negative 30. And I need it to add to negative 7. I need 2 factors of negative 30 that add to negative 7. That's negative 10 and 3. Negative 10 and 3 multiply to negative 30, and they add to negative 7. So what that does is it lets me rewrite negative 7x as negative 10x plus 3x. And now we can apply our grouping idea again. What can I factor out from that first half? I can factor out a 2x, and I'm left with x minus 5. The second half, what can I factor out? I can factor out a positive 3, and I'm left with x minus 5. So the factors of that quadratic term there are 2x plus 3 and x minus 5. Now look at the x to the 4th minus 1. This is the difference of perfect squares. It's x squared minus 1 times x squared plus 1. We need to get quick at recognizing that pattern. X squared plus 1 can't be factored, but x squared minus 1 is again the difference of perfect squares. So it's x plus 1, x minus 1. So our final answer, what are the factors of this crazy 6th degree polynomial? They are 2x plus 3, x minus 5, x minus 1, x plus 1, and x squared plus 1. The product of all of those factors together will give you this original expression up here. They're equivalent. They look different, but they always have the same value. Number 7, solve y squared minus 3y equals 9 by using the quadratic formula. So, hopefully you remember from 9th grade, the quadratic formula solves any quadratic equation for us, and it's x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Now, your quadratic equation needs to be set equal to 0. So, y squared minus 3y minus 9 equals 0. Go through and figure out what are your a, b, and c. That's your coefficients. Your a value is the coefficient of the squared term. The b value is the coefficient of the linear term, the plain old variable. Notice that b is negative 3. Take the sign with it. And c is minus 9. And now we just plug into the quadratic formula. We get y equals negative 3, so positive 3, plus or minus the square root of negative 3 squared minus 4 times a times c all over 2a. Y equals 3 plus or minus the square root of 9 minus 9 plus 36 over 2, just simplifying inside the square root. I get y equals 3 plus or minus radical 45 over 2. And hopefully you remember from 9th grade, we will review it in a couple of weeks, How do I simplify that square root? Well, 45 is the square root of 9 times the square root of 5. The square root of 9 is 3, so that's 3 radical 5. And our final answer is y equals 3 plus or minus 3 radical 5 over 2. Those are the solutions to that quadratic equation up there. Again, this was just a review of Algebra 1. We will need the quadratic formula eventually, just not yet. Factor completely. Whenever we factor, the first question we need to ask ourselves, is there a GCF? 4 and 25, there's not. X squared and x to the 4th, I can take out an x squared. Y to the 4th, that doesn't have any y's. This has a z, that doesn't. So I'm left with 4 y to the 4th minus 25 x squared z to the 6th, because I factored out that x squared. Now you need to look at this and say, can I factor this binomial? And the answer is yes. We can factor it as the difference of perfect squares, because that's 2y squared. Sorry, that's 2y squared squared, because I want y to the 4th, minus 5xz cubed squared. And now we can apply the difference of perfect squares identity. We get 2y squared minus 5xz cubed times 2y squared plus 5xz cubed. This is just applying the difference of perfect squares to something that's kind of crazy, something a little bit more challenging than we've seen before. 9, factor completely. 1 plus x to the 9th. Well, clearly this is not the difference of perfect squares, so probably it's related to perfect cubes. That's 1 cubed plus x cubed raised to the 3rd power. So I can apply the sum of perfect cubes formula to this, and we get 1 plus x cubed. Remember, it's always, the linear factor is 1 same sign x cubed times the first term squared, 1 squared, which is just 1, opposite sign, find their product, so 1 times x cubed is x cubed, always positive, that thing squared is x to the 6th. So we get 1 plus x cubed times 1 minus x cubed plus x to the 6th. Looking at this again, I have the sum of perfect cubes again. So I can factor that as 1 plus x, 1 minus x plus x squared. That's just applying the sum of perfect cubes formula to 1 plus x cubed times 1 minus x cubed plus x to the 6th. So factored completely, that's how I would factor 1 plus x to the 9th. And finally, show that this is an identity. Hopefully you remember this because we did this in class. It was on the homework for lesson 6. Show that this is an identity. I'm going to start with this side, and I want to make it look like 4xy. So there's 2 ways to do this question. You can look for and make use of structure and say, oh, wait a minute, that's something squared minus something else squared. So I can use the difference of perfect squares identity. So x plus y minus x minus y, that plus that term times the first term plus the second term. They're equivalent because I applied the difference of perfect squares identity. Simplifying inside, I get x plus y minus x plus y, distributing that negative 1, times x plus y plus x minus y. Just simplifying inside each of these parentheses here. X minus x adds to 0, so I'm left with 2y. Y minus y adds to 0, so I'm left with 2x. And we get 2 times 2 is 4 times x times y. So I started with that side and I ended up with 4xy. You can do this question by brute force and say I'm going to square that, and then subtract. And you're still going to get 4xy. But it's nice and nifty to look for and say this is really the difference of perfect squares.